Nobody knew what they were smelling. Bitter, sharp, like rotting cilantro, and then they saw them. Shield-shaped bugs blanketing the siding of homes across Allentown, Pennsylvania. It was 1996, and America had just met its newest uninvited guest. Haliomorpha halis, the brown marmorated stink bug, had likely arrived years earlier, hidden inside a shipping container from China or Japan. By 2010, it had quietly conquered 33 states. Today, it's confirmed in 47. Nobody saw it coming. By the time anyone did, it was already everywhere. The mechanics of how it damages a crop are simple and exact. The bug does not chew, it pierces. Using a needle-like mouthpart called a stylet, it punctures the skin of a developing fruit and injects digestive enzymes, then draws the liquefied tissue back out. What is left behind is a dry, corky patch beneath the skin, a defect orchardists call cat-facing. A single feeding session takes seconds. A single bug can feed on dozens of fruit in its lifetime. And the damage was not theoretical. In 2010 alone, mid-Atlantic apple growers lost an estimated $37 million to stink bug damage in a single season. By 2026, cumulative losses across tree fruit, vegetables, and row crops have pushed past $3 billion. The USDA's own estimates place national agricultural risk in the billions annually at the pest's peak spread. Federal and state governments responded with everything they had. Broad-spectrum pesticide programs were sprayed on a calendar instead of as needed. Pyrethroid rotations wiped out the beneficial insects already living in the orchard along with the pest. Pheromone-baited traps were installed by the thousands to monitor movement. Quarantine inspections targeted shipping containers at major ports, searching for stowaway egg masses before they ever reached American soil. The U.S. Department of Agriculture poured tens of millions of dollars into research programs, chasing a foreign solution, including years spent vetting a tiny parasitic wasp from Asia that regulators were too cautious to release widely. It did not stop. And then, somewhere around 2013, entomologists running sentinel egg mass surveys in the mid-Atlantic started noticing something they could not explain. Dr. Kim Holmer has spent most of his career at the USDA Agricultural Research Service, studying how invasive insects move through American farmland and what already living here might push back against them. In the early 2010s, he was monitoring stink bug egg masses pinned to leaves in soybean fields and orchard hedgerows across Maryland, Pennsylvania, and Virginia. He was not looking for a native predator. He was looking for parasitism rates on the eggs themselves. What he found was a numerical anomaly that should not have been there. In counties where the brown marmorated stink bug had been established the longest, the population curve was no longer accelerating the way the early models predicted. Something was eating the EGGs before they ever hatched, and something else was taking the adults and nymphs in numbers nobody had been tracking. Holmer and colleagues at Rutgers, Penn State, and the University of Maryland began documenting it properly. The papers that followed were understated in the way scientific papers are, but the data underneath them was not. Something was happening in the hedgerows and woodlots bordering these farms that no spray schedule, no federal trap program, no imported wasp was responsible for. In the same years, researchers cutting open stink bug egg masses collected straight off leaves in New Jersey and Pennsylvania found something one paper described in unscientific honesty as a wasteland. Egg after egg, hollowed out from the inside. In some fields, native parasitism alone was accounting for a meaningful share of total egg mortality, and that was before anything large enough to see with the naked eye had even moved in. What followed was a decade of sweep netting, sentinel egg placement, and gut content analysis that confirmed something Carl Mathis already suspected from the quiet in his orchard. Two separate native hunters had quietly stepped into a fight the chemical programs were losing. Two very different predators, working two very different stages of the bug's life, together closed the door on a population explosion. The first hunter was the EGG specialist, a tiny native wasp barely 2 millimeters long called NRM-PZ, already common across eastern North America long before the stink bug ever arrived. It had spent its evolutionary history parasitizing the eggs of native stink bugs, the green stink bug, the brown stink bug. Species farmers had lived alongside for generations. The female finds an egg mass by scent and touch, drills her ovipositor into a single egg, and lays one of her own eggs inside it. Her larva consumes the host egg from within before a single stink bug nymph ever has the chance to hatch. In the earliest invaded counties around Allentown, researchers documented native wasp parasitism rates on brown marmorated stink bug egg masses climbing year over year as the native wasp populations adapted to a food source they had never seen before but were already perfectly equipped to use. It is worth saying out loud what a stink bug egg mass cannot defend against. In its native range in Asia, Haliomorpha halis evolved alongside a specialist wasp, Trisulcus japonicus, often called the samurai wasp, a predator so precisely matched to this one pest that it parasitizes nearly every egg it finds. North America did not have that specialist. What it had instead was a generalist, Telenomus podisi, already wired to hunt stink bug eggs of any kind, needing only a new host sitting right there in the hedgerow. It did not need millions of years to evolve a new behavior. It needed only to notice the eggs were edible. But egg parasitism alone could not close the loop. Plenty of nymphs still hatched, still grew, still fed on fruit through the summer. Something needed to handle the bug once it was big enough to walk, fly, and feed on its own. That is where the second hunter comes in, and it is the one almost nobody expects: the praying mantis. Two species do the work in the mid-Atlantic: the native Carolina mantis, Stagmomantis carolina, and the introduced but long-established Chinese mantis, Tenodera sinensis, which has been part of eastern American hedgerows for well over a century and behaves, for all practical purposes, like a resident now. A mantis does not hunt the way a wasp hunts. It does not search. It waits. Anchored to a branch or a seed head at the orchard edge, raptorial forelegs folded and cocked, it relies on stereo vision and a strike speed measured in milliseconds. When a stink bug, nymph, or adult wanders within range, the mantis does not chase it. It simply closes the distance with a single explosive extension of the forelegs, and the bug is pinned before it registers a threat. Stink bugs are not defenseless. Their namesake glands release a sharp chemical deterrent that drives off most birds and many insect predators on contact. Mantises, it turns out, do not particularly care. Gut content studies and field observations across Pennsylvania and Maryland orchards documented mantises taking adult and nymph stink bugs at meaningful rates in late summer, precisely the window when the bugs are most mobile and most damaging to ripening fruit. A single mantis stationed at a hedgerow border over a season works through dozens of them, methodically, one ambush at a time. This is what makes the two-hunter system complete. The wasp thins the population before it is born, working eggs by the hundreds across a field in early summer. The mantis takes what survives to adulthood, working the orchard edge where the bugs stage before moving into the fruit. The wasp cannot touch an adult. The mantis cannot reach an egg sealed inside a leaf fold. Together, they cover the entire life cycle from the moment the egg is laid to the moment the adult tries to feed. If you walk a hedgerow bordering a Pennsylvania orchard in late August right now, you can see both halves of this story at once. Pull a leaf with an EGG mass off a soybean plant at the field edge and hold it to the light. Some eggs are pearl white and intact. Others are darkened, collapsed, with a small round exit hole where a wasp has already emerged. That is a parasitized mass doing its job before the season even properly started. Walk 10 feet further into the goldenrod and you will likely find a mantis, head swiveling, perfectly still otherwise, an ambush already set. It is worth pausing on what a mantis ambush actually looks like up close, because it explains why this predator works on a bug most other insects avoid. The mantis's compound eyes sit forward on a triangular head capable of rotating nearly 180 degrees, giving it a depth of field most insects do not have. It tracks a moving target the way a cat tracks a bird. Small adjustments, no wasted motion, until the prey crosses an invisible strike line. Then the forelegs fire forward and snap shut around the body in a motion that takes less time than a human blink. The stink bug's scent glands can still discharge after capture, and field researchers have noted mantises occasionally pause or reposition their grip when this happens, but the capture itself is rarely undone. Once those spined forelegs close, the bug does not get a second chance. There is a part of this story that growers did not expect either. Stink bug damage does not always mean a wasted crop. Cat-faced apples and corky peaches, the fruit too cosmetically damaged for the fresh market, are increasingly being diverted into juice, cider, and processing lines instead of the dumpster. Regional cideries across Pennsylvania and Virginia have leaned into exactly this surplus, turning blemished fruit that would have once been a total loss into a usable, lower-grade input stream worth real money to growers who would otherwise eat the loss outright. The damage the bug caused did not vanish, but some of it stopped being pure waste. There is a third piece of this story that almost nobody outside entomology circles ever hears about, and it has nothing to do with native species at all. For years, researchers debated whether to deliberately release the samurai wasp from Asia, the true specialist, into American fields. While regulators deliberated, the samurai wasp showed up on its own. First detected in Maryland in 2014, almost certainly arriving the same uncontrolled way the stink bug itself had. It is now established and spreading on its own timeline across the mid-Atlantic, adding a third layer of egg predation on top of what the native Telenomus wasp was already doing, entirely without a single permit or release program behind it. What makes the samurai wasp's arrival especially striking is how it interacts with the predator system already in place. Where Telenomus podaceae is a generalist working many different stink bug species at modest efficiency, the samurai wasp is a specialist tuned specifically to Haliomorpha halis, attacking egg masses at a far higher rate wherever its range overlaps. In counties where both wasps are now present, researchers tracking egg parasitism have found combined rates climbing well beyond what either species achieves on its own, a layered effect nobody designed and nobody funded, stacking quietly on top of the mantis predation working the adults at the same time. The result? Between two native predators already doing the work and one accidental specialist arriving uninvited, is a predation system more effective than any single program federal researchers spent years trying to design. Not because the solution was complicated, but because for nearly 2 decades, almost nobody thought to look at what was already standing in the hedgerow. Carl Mathis's orchard is not the only one. The same pattern is now showing up across Pennsylvania, Maryland, Virginia, and into the Hudson Valley of New York. In counties where the brown marmorated stink bug has been established for 15 years or more, fruit damage rates that once climbed every season are leveling off and, in some blocks, declining. Not to zero, but to a level growers can manage with far less spray than a decade ago. Extension agents working with orchardists in these counties now routinely recommend leaving hedgerows and field margins unmowed through late summer, the opposite of what conventional orchard management once taught, specifically because that uncut margin is where the mantises stage and where the wasps find their hosts. No quarantine achieved this. No imported wasp release program achieved this on its own. What achieved it was the slow, uncounted work of a wasp nobody noticed, and a mantis everybody had seen 100 times and never once considered an ally. It is 4 in the afternoon, back in Berks County. Carl Mathis is walking the hedgerow that borders his peach block, the one his father always left a little wild instead of mowing flat. He stops at a stand of goldenrod gone to seed and crouches down. A Chinese mantis sits motionless on a stem, head tracking him as he leans in, otherwise still as a fence post. A few feet away, a soybean leaf someone planted years ago as a border crop has a dried egg mass clinging to its underside, half the eggs showing the small, dark exit holes of a wasp long gone. He stands back up, brushes off his knees, and looks down the row of trees, fruit hanging heavy and mostly clean. The orchard didn't need rescuing, he says, more to the hedgerow than to himself. It just needed enough time and enough wasps and enough mantises we never thought to count. We spent $3 billion trying to spray the bug into submission. The hedgerow was already doing it. We just had to stop mowing it flat long enough to let the mantises take their stand. If you want more stories about the hidden ways the world around us is changing, subscribe. New piece every week.